Welcome back to Physics 246 Online. In this last section from Bevington and Robinson's book in Chapter 4, we're going to introduce a new quantity that's referred to as the chi-squared value. And this subject has to do with the chi-squared test of a distribution. We're trying to answer the question, how do we quantitatively assess the agreement between a distribution function that we assume the data comes from and the actual observed data? So the situation that we want to imagine is that we've got a histogram, which is in fact a frequency distribution representing our measurements. We make lots of measurements and we only get certain values for the measured quantity, and we get some of those values over and over again. So we postulate that those data come from a specific parent population distribution function. It might be a Poisson function, might be a Gaussian function. Usually it's going to be a Gaussian function. But our question is, how do we test whether that postulate is actually in agreement statistically with the measured data? So we use what's called the chi-squared test. And the chi-squared test is a comparison between the data and the function that we assume characterizes the data. So here's how it works. The chi-squared value is defined as a sum over all of the possible results that we get when we perform a measurement. And so the h here represents the frequency, the number of times that we get a particular result. The p is the assumed probability distribution function for those possible values, and n is the total number of measurements that we make. So the numerator is comparing the actual numbers of measurements that we make of a particular value xj, and then we subtract what is the expected value that we would get for a particular parent distribution function. That quantity is squared, and then we divide by the uncertainty in that particular value squared. And we sum this up over all of the possible values. So there's more detail on this function and what it means and what it's used for in Chapter 11, and we'll get there eventually in the course. But for now, let's just make sure that we understand all those terms that are in the function. So the h is the measured frequency, or the histogram bin, or the number of times that we observe that value x sub j, which corresponds to the value in that bin. N times p is the predicted number of observations, and sigma is the uncertainty. So here's that expression again. And what we usually do, since we don't necessarily know ahead of time what the uncertainty is in we don't know what the standard deviation is of the particular distribution function, we estimate the denominator term based on Poisson statistics. And so we imagine that even though perhaps the overall probability distribution function is assumed to be Gaussian, since each of the h values represents a number of times that we perform a measurement that gives us this value, so it's kind of a counting experiment, so that we can use the Poisson equation that tells us that the variance is the same as the mean value, or the value that we actually get in that particular bin. So that's what chi-squared means, and let's try to figure out what we expect it to be on average when we average it over all those data points. So imagine that on average, the term in the numerator were approximately 1 sigma. If that were the case, then the total chi-squared for n bins would be approximately equal to n, the total number of bins, or the total number of possible values that we would get. So statistically, we would expect for the chi-squared term something close to n, and in fact, when we take into account that there are a certain number of constraints on the data that we use, perhaps we use those data to extract the mean value, and that adds a certain constraint to the data, we're going to define this quantity nu, the Greek letter nu, to be the number of possible values minus the number of constraints. And so then that's what we would expect our average chi-squared value to be. So we already said what those were, nu and n sub c, and the textbook gives some illustrations, some examples to show how these numbers are actually determined. So what we then do, because we expect that the average chi-squared value should be this quantity nu, we're going to define a new quantity, no pun intended, which is the chi-squared value divided by nu. And so that is something that if the chi-squared value is equal to nu, we would expect this number to be approximately 1. This is called the reduced chi-square value. So chi-square by itself is that total that's summed up over all of the data points or the bins, and here we normalize it by dividing by the number of degrees of freedom in our data. So in doing the chi-squared test, here are the steps. Using the equation for which we define chi-squared, we calculate what it is for each data point, each of the terms that's in the sum. We sum all of the individual chi-squared values. That gives us the total. We figure out the number of constraints and take the number of data points minus the number of constraints, which is nu, and calculate the reduced chi-square, which we expect if the data actually represent a good fit to the parent distribution function, we expect that reduced chi-square value to be about 1. And that's the question. Once we calculate the reduced chi-square, we compare it to 1. And then we think a little bit, based on those comparisons, what conclusions can we draw? What can we say if our reduced chi-square value is approximately 1? What, on the other hand, might we conclude if it's either much, much greater than 1 or much, much less than 1? So we can talk about some of these things in class. And since this forms the basis of a homework problem, I want you, as you read the book, to think a little bit about what the possible conclusions might be. One pretty obvious thing is, if the reduced chi-square value is approximately 1, then that means that the data form a good representation of that assumed distribution function. But what might be happening in either of these two extremes? So that's the introduction to this topic of using the chi-square test. We're going to come back to it later on in the course as we assess how well our data are fitted by a particular kind of fitting function, which is just a little bit different situation, but very similar. So we'll see this again, and hopefully this helps explain a little bit about what the chi-square value is.